Now to the required rated currents for the employed inductor in a buck converter. So last lecture essentially, or last video, we have discussed how to determine the required inductance, and that's basically we define the inductance such that we avoid the negative current. However, there are two rated currents that we need to calculate in order to be able to order the inductor and use it in our buck converter design. The first one is the RMS current rating, and then the second one is the core saturation current. So as I mentioned before, inductors are made of copper or a conducting material. So basically, as you increase the current flowing into them, or the RMS value of the current flowing into them, at some point the RMS current square times their equivalent series resistance will cause a lot of heat that the wire will melt, or essentially the temperature will reach 125 degrees C. As you can see in this figure, for example, the inductor on the right and the inductor on the left, both of them have the same inductance value. However, why this inductor is very large? Well, you can see that the wires that this inductor is made of are very thick, so its ESR is small and it can essentially handle a higher amounts of RMS current rating. So actually the inductor on the right has an RMS current rating of 30 ampere RMS, while the inductor on the left has a rating of 2.2 ampere RMS. Okay, so another thing is size of an inductor infers its RMS current rating. If you find two inductors of the same inductance, however one is much larger than the other, then this means that the larger inductor most probably has much higher RMS current rating. Now, if we look into the data sheet of an inductor, we'll find that it provides the RMS current that causes 40 degrees C temperature rise. And the whole idea is, like typically we assume, or component manufacturers assume, that the nominal operating temperature of the converter is around 85 degrees C. And then if the RMS current that's flowing into the inductor causes a heat due to its equivalent series resistance that causes 40 degrees C temperature rise in its surrounding, or its surface temperature, 40 degrees C, this leads to what? 125 degrees C, which is the maximum temperature a power converter can operate reliably, at least in the commercial level. Okay, so my point here is the RMS current rating of an inductor in data sheet, you will not find it. Typically, it's not saying RMS current rating. They give you either the 20 degrees C temperature is RMS current that causes 20 degrees C temperature rise, or the RMS current that causes 40 degree C temperature rise. Okay, and basically in our class, or in this video, we'll consider that the RMS current that causes 40 degrees C temperature rise as the RMS, or the maximum RMS current rating of the inductor. And of course, we should select the inductor. Like whenever we select an inductor, we have a certain inductance. We need to make sure that this inductor will be able to handle the high currents of the buck converter we are designing. And so we need to calculate the RMS value of the current flowing into the inductor. And as I mentioned before, the current of an inductor has a triangular waveform, essentially a triangular periodic signal superimposed into a DC component. And since if we separate both, so we have a DC component and then we have high order harmonics. So essentially the RMS current value of the inductor root mean square. So essentially if we took the square of that value, we are looking for the mean square. The average is 1 over t, 0 to t, where t is the cycle time, times the, and then we integrate the inductor current dt over, square over cycle. So essentially we integrate the square value of the inductor current over a complete cycle from 0 to t, and then divide by the cycle tmt. This will give us the RMS current square. So if we do that, we'll find that the RMS current of this triangular signal superimposed over a DC is equal to I out square plus 1 over 3 delta IL over 2 square. Obviously, the DC this represents the DC, while the triangular exchange represents the higher order harmonics. And since DC is orthonormal compared to or in relation to the higher order harmonics, essentially we'll find the RMS square is basically the DC squares, and then we calculate the RMS value of the higher order harmonics alone, which gives 1/3 of the amplitude of the triangular signal. Delta I over 2 is basically the amplitude of this triangular signal, where delta IL is the peak-to-peak value of the inductor current. So delta IL, square it and take 1/3 of it, that's going to be its RMS value square. And so after we design our buck converter, after we select the required inductance, we calculate its RMS current using this formula, and then we go online and look at which inductance, say we select 10 microhenry, which 10 microhenry inductor is going to has an RMS current rating that's higher than the one we calculated, okay, via this equation. Now to the core saturation current, that's the second rating, okay. So typically air core inductor, if you just bring a wire and then you wound it say around a pencil or ceramic or a dielectric material that's not ferromagnetic essentially, we call it air core inductor. So you will find that, say, in Coilcraft, this supplier, you will find that they have or they provide air core inductors. And by air core, it means that the inductor is essentially wounded around a ceramic material or plastic material, so essentially non-conducting or a material that's not ferromagnetic. And you'll find that the value of the inductance is low, about between 5.5 nanohenry up to 1 microhenry, maybe up to 5 microhenry, so it's low. So how do we achieve higher values of inductance? Well, the secret is to put, for the same geometry, this same inductor that we rolled, say, around the pencil, however, the inductance we get is, say, about like 0.5 microhenry. And we want to make the, how, if we just bring a piece of ferromagnetic material and put it inside the inductor, and we measure the inductance, the resultant inductance, for the same geometry, the same number of turns, you will find it maybe 500 microhenry. So the whole secret to achieve higher inductance in the same volume size with the same geometry, same number of turns, is just use a ferromagnetic material. So what is the secret? Why ferromagnetic core or ferromagnetic material essentially boosts the inductance, say, from 0.5 microhenry up to 1,500 Henry microhenry? By the way, the boost factor is equal to mu r, where mu r is the relative permeability of the core material, the ferromagnetic core material, which is between 1,000 and 5,000. So when in this example, I assume the mu r is equal to 1,000, but it's very easy to achieve 4,000, 5,000 value. So why this happens? Before exploring the reason, I like just to clarify or point out that an air core inductor, the schematic symbol is just a coil, right? For a coil or a solenoid with a ferromagnetic core inside, its symbol, we just add these two parallel lines which indicate it has a core inside. So why when we bring the same coil, the same geometry, the same size, and we just insert inside a ferromagnetic material, there's a dramatic increase in the inductance? Well, the whole idea is, let's see, if we apply current IL, we know that this coil is going to produce magnetic field according to the right hand rule, right? And as we increase the current as shown in this plot, what will happen to the magnetic field? The magnetic field is going to increase linearly. Okay, assuming this is a very the length of the coil is much larger than its diameter. And as we know, the inductance, the self-inductance of a coil or a coil is proportional to the ratio of B over IL, which basically is the slope of this line. So once we insert the ferromagnetic material inside the coil as shown here, and for the same current IL, we'll find that the slope has increased by a factor equal to mu r, or this point has been boosted mu r times. So why this happens? Well, if we zoom into or inside this ferromagnetic material, we'll find it consisting of tiny magnets that basically are randomly placed inside the core. So what will happen is the net magnetic field coming from them will be zero. Now, when you start to insert current, the coil, the conductor, the copper coil will produce magnetic field. And this magnetic field, what will happen? Essentially, it will start to align the tiny magnets that are inside this core. So it will bring this tiny magnet from left to right, and will bring this one into this direction, and so on. So it will start to align the magnet in the same direction. And so these tiny magnets that are inside the core material are going to produce net field. Instead of being B0, B now will have a value that adds it to the original magnetic field that's produced by the copper coil itself. Okay? And so the net field, essentially both the fields produced by the coil and the field produced by the tiny magnets that are inside the core due to their alignment, will produce a net field that's much larger, mu r times the original field that essentially in the coil if it's air core inductor or air core coil. Okay, so that's why ferromagnetic material is able to boost the inductance of a coil for the same volume size and geometry, by a factor mu r, relative permeability of the core material that ranges between 1000 to 5000 times. Now to the saturation current, core saturation current. So as we increase the current, as you can see inside this coil that is fitted with a ferromagnetic material, we'll find that the magnetic field keep increasing until at some point all of the tiny magnets that are inside the core material are pointing exactly in the same direction. So we already squeezed out, or we got all the fields that we can get from all these tiny magnets that are inside the core material. So essentially the magnetic field will start to saturate and you get the same slope as in here. Okay, so remember, air core inductor, it doesn't have saturation field. It doesn't have, core saturation current. Obviously, it doesn't have a core, so it will not have a core saturation current. On the other hand, a magnetic core inductor, like the one shown here, or a coil that's fitted with a magnetic material, ferromagnetic material, will have a core saturation current because it has a ferromagnetic core. Now, what is the definition of the core saturation current? It's basically the current that essentially will cause the inductance of the equivalent inductance of the coil to decrease by 10% than its zero inductance. So at origin, when the current is zero, you have the highest inductance. Basically, as I mentioned, the inductance is proportional to the slope of the line, right? So at this point, the slope or the ratio, as you can see, the slope has decreased by, say, 10% essentially. So the definition of the core saturation current is basically the current that causes the inductance, the equivalent inductance, to drop from its value around zero current by 10%. So remember, an inductor has two current ratings, the core saturation current as well as the maximum RMS current rating. An interesting, at some points you will find that the RMS current rating that causes 40 degree C temperature rise is lower than the saturation current. So in this case, the rated current is set by the RMS current rating of the inductor. In some cases, some other cases, you'll find that the saturation current happens before the RMS current rating. So in this case, the core saturation current defines the maximum current that this inductor can handle. Okay. So remember, there isn't a rule, but we don't use both as a rating. We just select the smaller one as the maximum current that we should use. Saturation current is an absolute value. RMS current is an RMS value. All right. And so actually, from coilcraft, all these inductors are in the same volume size, occupy the same geometry, the same volume size. So, however, as you can see, the inductance is increasing due to using different ferromagnetic materials. You'll find that the saturation current, the core saturation current, is going to be higher than the RMS current in here is 30 ampere or around 28 to 30 ampere, always constant, right? While the saturation current, as we increase the inductance, we use a core material of higher relative permeability, and so essentially within the same volume. So essentially, we'll find that the saturation current decreases, and at very high values of inductance, 33, say in this specific example, 33 microhenry, the saturation current is 2 ampere, which is much lower than the RMS current rating of the inductor, and so this sets the maximum current that we can use this inductor for. On the other hand, for 1.5 microhenry for the same volume, the same dimension, we'll find that the saturation current is 100 ampere, which is much higher than the RMS current rating. So the RMS current rating defines the maximum current that this inductor can handle. And as I'm mentioning here, and as shown in this plot, for the same volume size, same dimension, same volume size, you'll find that as you increase the inductance, what will happen is the saturation current, basically the current at which the inductance starts to decrease, essentially decreases.